Let's continue with a look at bastion host systems. Now, a bastion host system may also be referred to as a hardened system. In other words, it has its defenses strengthened to defend itself better, isolate itself better from the bad guys that are attacking the server. Basically, we will implement the bastion host system on any computer or appliance that is publicly exposed. That would be your firewalls, DMZ or perimeter network, any system that has high value applications or high value data that it might be working on or holding. So any of these systems would be your bastion host systems. Typically, our goal is to reduce the attack surface of that computer. In other words, take away the angles that the bad guy might use to attack you. Reduce the vulnerabilities of that system to as low a level as we possibly can because of its high value or its high exposure. I want to reduce that attack vector, that attack surface, and minimize the opportunity for the bad guy to be able to break in. How do we do this? Well, it starts with, usually we'll make these systems dedicated to one or perhaps two services maximum. I don't want to take a system that's publicly exposed and put 19 different services on it, because each service is implemented in software, and that software has vulnerabilities. It has bugs, opportunities for the bad guy to break things, to break in, to compromise the system. So I make it dedicated purpose, one or two services only, like it'll run web services and maybe DNS services. But even that is probably not likely. Probably I'd make that two boxes, two separate computer servers, one for web services and one for DNS services. The fewer number of services, the fewer amount of software running, the fewer vulnerabilities. And if a bad guy does decide he's going to target this box, he's going to break in, he only gets one service. If you put 9 different services on one box and he breaks into one of those 9 services, he now can compromise all 9 services. But if you only have one service on the box and he breaks into that service, he gets the one service and he has to break into 8 more boxes in the previous example. So dedicated purpose, only 1 or 2 services provided. These systems will be patched very, very often. Now, we typically will patch all of our systems very often. We're going to pay particular attention to these boxes because those patches, those updates that we get from the vendors for the operating system, for the applications, and maybe even for the firmware on those systems, those come out regularly, and I want to be sure that these boxes get patched in a timely manner as quickly as possible. These would be your first ones to be patched after testing and approval. And these would also be the ones that I would verify that the patch has been applied and applied successfully. Next, I'll minimize the users on the box, especially those with a high level of privilege. So use the fewest number of users possible, bare minimum number to sustain the box, and also minimize the permissions, the privilege level. They call this the principle of least privilege. I will be especially diligent applying the principle of least privilege on these boxes. We talked about reducing the number of services. Disable or uninstall any unnecessary services. Don't just think about what I need it to do, so I'm going to install the DNS service. I'm now going to look at that box as it installed, and I'm going to remove many of the services or applications that got installed automatically. I don't need them on this box. Kill them. Get them off the box, because any software that's running increases the attack surface. If you don't need it to be running, stop it. Get it off the box. We talked about deleting unnecessary software. Always add a personal firewall to these boxes. Today, most systems include a personal firewall. Be sure the personal firewall on these bastion host systems is installed and active and configured correctly. Next, I'll install antivirus, anti-spyware, anti-malware, whatever you want to call it, all these defenses against malicious software. And of course, those types of protections require regular updates, and they typically will implement routine scans. So be sure you are very often updating those signatures of the malware, and that you are very often performing as full a scan as you can afford to run. I might run host intrusion prevention system on these boxes as well. In other words, look for a series of packets that form an attack. Look for malicious behavior on this system. If a process is assembling an executable file and installing it as a service, man, this is a bad thing. This is a danger Will Robinson. This is red flags should be waving. So we want a host intrusion prevention system installed on these boxes as well, very much like the antivirus. Another tool that is commonly used on these Bastion host systems is an external vulnerability scan. This is a system that is not the Bastion host, but some secondary system that we point at the Bastion host system and have this system interrogate that box to see what a bad guy would see and look for the vulnerabilities that a bad guy is looking for. So externally, I'll run a vulnerability scanner on my Bastion host system to identify the vulnerabilities that a bad guy might be able to identify. And finally, I might implement operating system integrity verification. Now, this is done more and more. It's still relatively new, but there's a new piece of hardware that's being installed on many enterprise-level systems called a Trusted Platform Module chip, a TPM chip. And this TPM chip can actually take fingerprints of your critical core operating system files and other configuration parameters. And on boot up, it will go verify the integrity of that file and that configuration. And if it finds any problems, any deviations from what it knew as its trusted boot up state, the system will simply fail to boot up. And we might also run these integrity verification procedures on the system while it's running. In other words, I knew that I configured this guy to point to the DNS server at 10.10.10.5, and if its DNS server is pointing anywhere other than 10.10.10.5, notify an administrator immediately. Someone has altered the configuration, and this would be an attack vector. So again, these are many of the things that we will do to establish what we call the Bastion host system, also called a hardened system. And again, any system that is high value, either processor data, or is publicly exposed in a high risk environment, we want to harden those boxes, make them Bastion hosts. These are many of the things that we will do to strengthen the security of these machines. We'll knock off here for now, and we'll pick up shortly where we left off. In this lesson on our networking infrastructure series, we're going to be looking at the endpoint systems. Now, these are the client-side systems that are attaching to our enterprise network environment, and we're going to look at how we might secure those devices. So let's start with a summary of what are these devices. Well, they start with the desktop computer, and that would include laptop computers. These are the workstations that our users are going to be spending the bulk of their day on. But today we're getting more and more of these bring your own device type devices, like pad devices and handheld devices. Cell phones even would fall into this category in some instances. Now what this says is we're starting to lose control over the operating systems and the configuration of these devices that are attached to our enterprise network. Typically it had been just desktop computers with the occasional laptop. Now we're seeing a pretty good split of those two between desktop and laptop computers, and we're adding to it cell phones, pad devices, and other handheld type of computing devices. So we have a great deal more opportunity for non-secure configurations, for bad software, malicious software that might find its way onto our corporate network, things along these lines. And so we have heightened concern these days over these endpoint systems. Now, these endpoint systems need different forms of administration. I don't want to have to walk to 4,000 computers and reconfigure some IP address or some firewall setting. I want to be able to do this from some remote location with some centralized tool like a policy. And so here we need remote access for administrators to be able to get to these boxes, to reconfigure them as appropriate, but not have to go to that box physically. So that's remote access and for the purposes of remote administration. And then remote administration en masse is typically deployed by a policy, usually through directory services. And I can apply policy based on organizational group, on domain, on site, as well as several other options. But depending on the type of systems that you're using for deployment of these policies, you may have a great deal of flexibility and be able to identify different types of handheld devices, like different types of cell phones, different types of pad devices, because each pad device requires its own software and its own specialized configuration with its own specialized vulnerabilities and security concerns. Now, something else that we can do from an administrative standpoint is deploy desktops from a centralized location. Now we would use something like a thin client at each workstation, at each cubicle, if you will, that has no real intelligence, no real operating system of its own, like we would think of an operating system, Linux or Windows, for example. It would just have enough of an operating system to boot up, connect over the network to the virtual platform, and then that platform would feed down a desktop. And basically it's like the image of a desktop, the screen capture from a desktop for this user session. And now I only have to manage and maintain that image file that I'm pushing out my desktop image to all these thin clients. I only have to maintain that one copy rather than maintain 4,000 copies, because each client is going to get their own copy of that one image. So it simplifies my administration if I can use the virtual desktop. Now this is referred to as platform as a service, part of a cloud functions. Now we're getting into cloud services, and platform as a service means I'm going to push down your operating system from my virtual environment, from my cloud environment. I don't have to push down the entire desktop. Perhaps you have your own desktop, and I can provide you access to a specific application virtually without installing that application on your computer. In other words, I have one copy of, let's say, Microsoft Office that I'll install and maintain on my virtual servers. And then when you want to run Office, you'll double-click an icon that I've put on your desktop, but that connects up to my copy of the application, and you actually run Word from my server, not from your workstation. This says I don't have to patch 4,000 copies of Microsoft Office. I patch one copy, and I can keep it very well maintained. I don't have to worry about some client out there who hasn't been doing his patching, and as a result, we have increased vulnerability on that system. Now, very often, I'll want to harden these boxes, these endpoint system, client systems, as much as I possibly can, and still provide the required functionality. Service is always balanced against the required functionality for that box. So what I'll do is I will see to it that we have regular patching implemented for all these different types of endpoint systems. I will harden them to the best of my ability. That means I'll install a minimum level of software in order for you, the worker, to do the work you have to do, but not much more than that bare minimum. I will assign permissions following the principle of least privilege. If you don't need to be an administrator to run your workstation, I'm going to keep you as a standard user. If you don't need full control over those files, I'm going to give you read-only control over those files, for example. Just the bare minimum of privilege. I'm going to install a host-based intrusion detection or intrusion prevention system, perhaps, and this helps to identify malicious behavior, aberrant behavior, suspicious behavior on a system, and might quarantine those processes and protect me from some sort of compromise. From an administrative standpoint, I can write policies that say these are the things you're allowed to do with the computer and these are things you're not allowed to do with the computer. And then I'm going to teach you about those acceptable use policies through awareness training, and I'm going to make you sign an agreement that says, yes, I understand the things I'm allowed to do and the things I'm not allowed to do with your computer. And that combination of acceptable use policies and awareness training provide me the justification to enforce my policies when they are violated. In other words, I can now reprimand, I can now punish if there is a breach of our policy. On these endpoint systems, I almost always will include antivirus, anti-spyware software, and I'll perform regular updates and regular scans. I'll install a minimum level of services, and I'll disable anything or actually uninstall or remove software for services that I don't need that endpoint to perform. I'll implement a minimum number of user accounts on that workstation. I'll install a personal firewall and be sure it's enabled and configured and updated. and I'll implement some form of configuration management. In other words, I'll isolate the user from any of the configuration dialogues that he shouldn't get to, and I may actually go verify the integrity of configuration parameters. And if I find that they've been altered, now I will go reprimand and I'll figure out how did this get changed, and I'll punish whoever it is that caused the change. By the way, it may not be the end user's fault that a configuration detail has gotten changed. It might have been an indication of a compromise or a breach, and this is something I'd want to know as quickly as possible. So this has been a review of the endpoint systems and how we might secure them in an enterprise networking environment. We'll take a pause here and we will continue in just a few minutes. In this lesson, we're going to look at virtual machines. Now, virtualization has been a really hot topic lately. This is a very fast-growing and very rapidly deployed technology in the enterprise. Virtual machine takes a single piece of hardware called the bare metal. That would be the actual physical PC, like a server class machine, and it would then have an operating system installed on it. Now, it might be Linux-based, it might be Windows-based, something along these lines. So that's the standard computer that we would install. And then on that computer, we might install various applications. As we see in the diagram, we have the bare metal down at the bottom, then the host operating system as the next layer up, and off to the left, we see several applications that we can run on that standard computer. And that's a fine thing. However, virtualization requires another layer at the application layer called the hypervisor. Now, what this hypervisor does is it simulates the resources of a computer and supports the installation of a guest operating system as an independent virtual machine. So that guest operating system needs a CPU. Well, the hypervisor says, here's your CPU, I have your CPU. The hypervisor doesn't have a CPU. It will actually commute that call for CPU down to the actual physical bare metal hardware through the operating system and use the physical CPU of that real physical box. The guest operating system has no clue it's actually in a virtual environment, that the hypervisor is pretending to be all those physical resources when actually he's just the middleman who says, yes, here's your printer port, hand me your rendered print job, and then the hypervisor will turn around and hand that print job down to the host operating system where the real printer port is attached. The hypervisor simulates these physical resources to the guest operating system. Then on that guest operating system, I can install multiple applications or services as needed. And as we see here in the diagram, we show 3 different virtual machines, each running different series of applications. This is great for increasing the utility of your hardware. Many systems operate at 10 to 20% utility. In other words, you're wasting 80% of your computer because you're only using it for a single desktop and a single series of applications for that one session. So if we install the hypervisor and virtual machines, those machines now will have their operating systems and applications and sessions that are running, and we are now more fully utilizing that physical hardware, the CPU, the RAM, the hard drive space, and then other resources that we might attach to that system, and providing those resources of availability to the guest operating systems as well to the local host operating system. So we are greatly optimizing system capacity. I can reduce the amount of hardware that I have to buy as well. Instead of having to buy, in this example on the diagram, I would need 4 different pieces of hardware. Well, that's a lot of cost, and that's a lot of space, and that's a lot of electricity. I can do all this on one piece of hardware, reducing that cost, that space, that electricity, that heat dissipation problem. I can use the virtual machines to isolate processes. Suppose the virtual machine number 1 has top secret data and processes operating on it. Well, then I can use the virtual machine 2 for secret data and processes, and virtual machine 3 for confidential applications and data. And you see how I can use the virtual machine as the boundary to isolate these different levels of sensitivity or trust or value. And I can isolate these processes for these various reasons. Perhaps they're different cost centers. So I have VM1 for one cost center, VM2 for a different cost center, and I can track the usage and then bill those cost centers accordingly for their consumption of my resources. It also supports a high availability and easy disaster recovery because the virtual machine now lives solely in software, and I can actually clone that software, take a snapshot of it, and if this particular virtual machine gets corrupted, I can simply point that virtual machine over to the copy, fire up the copy, and I can be back in business in a matter of seconds instead of perhaps a day or two to repair the hardware, reinstall the operating system, reinstall all the applications, restore data from the backup. I can take that snapshot in just a few minutes and I can restore it in just a few seconds in many cases. So it's great for high availability needs and easy disaster recovery. In addition, I can easily scale up my number of virtual machines by simply cloning them. I need another DNS server. I need another DHCP server. I simply copy the files that are the virtual machine and boom, suddenly I have a brand new virtual machine. It also supports the use of different operating systems on one hypervisor. So I've got a great deal of flexibility. Suppose I need 4 Windows servers and 8 Linux servers. I can do that on one piece of hardware using a hypervisor. This is the way most data centers are going today, and this is the way most cloud systems are implemented, through the use of a big piece of hardware with a hypervisor and then many guest operating systems or virtual machines. Continuing on, we're going to look at the different levels of service that these virtual machines provide. We have infrastructure as a service, where our virtual machine is operating more as a network infrastructure appliance. Remember, these infrastructure systems are very often going to be bastion host type hardened systems and dedicated services like routers, firewalls, and other infrastructure services. So I can implement my infrastructure in a virtual environment, again, for easy recoverability, disaster recovery, things along these lines, scalability, etc. Next, we use platform as a service that allows me to configure a series, one or more database servers like SQL Server, for example, and clone it in a virtual environment to improve scalability and disaster recovery and capacity. Application servers, web servers, etc. This is a platform as a service. Now, in addition, platform as a service, depending on whose definition you're looking at, may include virtual desktops that are spawned down to client workstations or client thin clients, dumb terminals. So that virtual desktops that we see software as a service might also be considered platform as a service, depending on whose definition you're looking at. So don't be surprised if you see that guy fall into one of those two categories. Then software as a service is the virtual desktop, virtual applications that we spawn. In other words, I have one copy of your graphics editing software that I maintain, and I don't have to install it on the 300 workstations out there. I only have to maintain the one copy. When you want to launch that application, you double-click an icon on your desktop. That reaches across the network, and I feed you your application over the network without ever having to install it on your machine. So I have to maintain one copy of the application, not 400 copies. Now, these virtual machines are commonly used for cloud environments, for HoneyNet, which is used as a defensive and learning tool in a corporate environment, mostly a highly sophisticated environment. HoneyNets aren't all that common, but basically it's an attack environment to draw the bad guys over there to the HoneyNet and away from the real resources. We use virtual machines for our testing and quality assurance labs to be sure that our applications are working as we expected, that the client side of it is connecting properly, that the patches we apply don't break other services or applications. Now, the hypervisors are being provided by many different companies today. One of them is VMware. One of them is Microsoft's Hyper-V. Oracle produces something called the VirtualBox, and there are many other hypervisors that are available. Some of them you have to pay for. Some of them are free, and you'll need to make that decision based on your budget and your needs and what your policies will allow. So this has been a lesson on virtual machines. We'll stop here and we'll pick up later. Continuing on with our lesson on networking infrastructure, we're going to take a quick look at mainframe computers. What is a mainframe? Basically, this was used primarily in the day where the computer occupied an entire room. One machine consumed a whole room, and it was the sole source of computing power and storage and anything related to the actual processing of data. This is the one place where we had a real computer. But we couldn't get all the users in that one room because the computer pretty much occupied it, and we didn't want that many people bumping around on this one very expensive system. So what we would do is install thin clients, also called dumb terminals, wherever we needed them. And they could be in the same building, in the adjacent room, or perhaps across WAN links or other remote access connections. So we could distribute them wherever we needed these thin clients, and then provide a connection path from the thin client to the mainframe itself. And this allowed many, many users to actually access the mainframe and get their work done, input their data and retrieve their result back from the mainframe. So the thin client was not an actual computer. It really had no CPU of its own. And basically it was just enough of a machine that would allow the system to boot up into some fundamental rudimentary operating system. It would install a network stack and a network interface card driver so that we had connectivity back to the mainframe. And it had a keyboard and a monitor, but it didn't have any local storage and it didn't have its own internal CPU. It basically was a window that connected the user to the mainframe. And then keystrokes would go up the stream to the mainframe, and the mainframe would send either characters back or might send screenshots back to the client computer, the thin client. No processing was done on the thin client. All the work was done back on the mainframe. Now, the way the mainframe would access these clients or give each of these clients a turn is through a polling process. See, the only intelligence in this network environment was in the CPU. However, we might have 100 or 1,000 or more users that periodically would need to access the CPU. So in order to give everybody an opportunity to use the mainframe, the CPU itself, the mainframe itself would reach out to each client one after one after one and say, do you have something to say? No, you do? Okay, transmit. I'll start working on that. I'll come back to you in a little while. Go to the next guy, go to the next guy. So through a polling process, the mainframe would query each client and see if that client had something to send upstream to the mainframe computer. This is a terribly inefficient way to share the utility of that mainframe, but there was only one device that had any intelligence to make a decision about whose turn it was to transmit or receive data. So that's how it was managed. Now, the mainframe would have a series of applications installed, but those applications would only be installed during the boot up process in a phase called the initial program load, the IPL. So if a bad guy were going to steal computer time, the bad guy would need to get his program listed on the initial program load script, and then the application would be available for his use and access. And again, this was often done to steal computer time because these systems would hire out time windows to various clients. Well, if you didn't want to pay for it and you wanted to steal it, your program listed on the IPL, and then you'd have to get that initial program load to install. Well, that thing only fired off during boot up. Anytime that the mainframe rebooted, which triggered the initial program load script, that was the time where the bad guy could inject his program that was stealing computer time. Now, these boot ups or IPLs were scheduled because we'd schedule the downtime of the mainframe, and that way it was predictable. You wouldn't be in the middle of some big processing job and we're suddenly going to shut down the box to perform some maintenance or repair. And as a result, the IPLs, the boot up, was scheduled. If a reboot occurred in an unscheduled fashion, this was a cause for red flags. What the heck just happened? That wasn't supposed to boot up right now. And is somebody trying to steal computer time by getting their data, their program loaded during the IPL, the unscheduled IPL? So this was the major threat to the mainframe computers. With this, we'll take a break here and we'll pick up where we left off.